Okay, I guess we're up and running here. Let's talk about hypothesis testing. This is the first of the Chapter 5 videos, a little late getting up this year. Let's talk a little bit about this. This is from Chapter 5, OpenIntro Statistics, 2nd edition. So all hypothesis tests have certain things in common. They have a sample observed value, in other words, some sort of a statistic that you've calculated from your sample, and you're trying to put that in context. So the hypothesis test method of doing that is to imagine a null hypothesis expected value. So a value that is expected if your theory doesn't work, if it's total crap, if it's wrong in some way. Rather, the devil's advocate position. So this is what should be expected if the null hypothesis were true, if you're wrong. And this is what you found from your data. So you put those two things together and you try and guess whether you're right or not in a really roundabout, backward way. You calculate the difference between those two things, and since you're assuming that the null hypothesis is true, you're really saying, in the world of the null hypothesis, how deviant is my sample? How unexpected is my sample value? And you turn that into standard error units, which allow us to look up values from the sampling distribution. So the benefit of that is that we can compare our sample value to all possible other sample values that should have happened if the null hypothesis were true. And that tells us how likely our sample value would be to happen, how unexpected it is if the null hypothesis is really true. And based on that, we make a decision about the null hypothesis. If it's very unexpected, if the probability of this happening, of our actual data happening when the null hypothesis is true, is low, in other words, if the p is low, the p-value is low, then we reject the null hypothesis. Otherwise, we don't reject it. We fail to reject it, we retain it, etc. And that's the only decision you make. You don't really make a decision about the alternative hypothesis, but at least not within the framework of null hypothesis testing. But we often take one extra step and say, therefore, since we've rejected the null hypothesis, I find support for the alternative hypothesis. Or, since we did not reject the null hypothesis, we failed to find support. We didn't support the alternative hypothesis. And then you make your conclusion, and you do that in terms of the original question. You say, so we can see then that there is not any difference between the athletic abilities of UTPA and UTB athletes, or something like that. Whatever the original question was, you turn back to that. So the procedure involves specifying both hypotheses. A lot of these you don't need to do if you're a super master amazing hypothesis tester, because frequently you know what you're doing and you don't have to go through these extra steps because you have them in your head. But at this point you do not have them in your head, I'm going to confidently say. So do them, especially the graph. So you draw and label a graph or a diagram. If we're doing a z-test, which we'll do first today, you find z critical, the critical value. It's the z to beat. You're going to turn your sample mean into a z-value within the null hypothesis sampling distribution of means, for instance. And you need to know how big should that z be before you reject the null hypothesis. Well, the answer is z critical. If your z is bigger than, if you beat z critical, it's not always just bigger. But if you beat z critical, then you reject the null hypothesis. So to find out if you can do that, you have to do some math, calculate z observed, cute little formulas for that. You compare those two. And if z critical has beaten, or sorry, z observed has beaten z critical, in other words, if its absolute value is larger and if it's in the correct direction away from the mean of the null hypothesis, then you reject the null hypothesis. And then you state your conclusion. So the technical part actually isn't very difficult usually. It can be a little funky, but honestly, the more confusing it gets, the more likely we are to just use a computer to do it. You need to understand some things about it to make it work, but in general, we use computers to do the really complex stuff. There's nothing that complex in this class, but really complicated stuff we just use computers for. Our z-observed value, every hypothesis test is going to have something that's kind of like z-observed. It's going to be some standardized value that we're going to put into a sampling distribution and compare to the null hypothesis standardized value. So that always involves taking the point estimate, whatever the sample value is. If we're looking at means, then this is the sample mean. If we're looking at differences between means, this is the difference between two sample means. Whatever it is, we condense it down to one value. So 2 means, we take the difference and use that to condense 2 values down to 1 value, for instance. We condense that to 1 point estimate, and we compare that to what that estimate should be if we're wrong. So the devil's advocate position, the worst case scenario. So how different is this from the worst case scenario? And then we divide that by the standard error, and what that does is that takes this difference and puts it into a common metric, into a standardized number system that we can use to look up areas. And the reason we want those areas is to say exactly how unlikely our observed point estimate is if the null hypothesis is true. Yeah, that's calculating the observed. So some of the questions that we have that will help you get grounded as far as this process. What is the sample point estimate? What kind of statistic is it? Are we looking at means? Are we looking at is the estimate a regression function? Is it a correlation value? Is it a difference between two means? Is it the difference? Is it the mean of the differences in a paired sample test? Whatever it is. And then whatever population it estimates is usually a direct carryover from that. If you're estimating if your sample statistic is a difference between two means, well then the population value is the difference between two population values, population means. So there's usually a direct, almost a one-to-one correspondence there. So what's the sampling distribution of that? Well, if you can think of what individuals comprise that sampling distribution, then you can think of what are all the possible things that are similar to your mean, or to your sampling point estimate, which is, we'll start out with just saying it's a mean for right now. What is the mean of the sampling distribution? With two-sample tests, it's really easy because it's just 0. For confidence interval problems, it's always the point estimate itself. So the confidence interval for the mean, you just construct the confidence interval around that sample mean, pretending that that sample mean is the population mean. For two-sample problems, it's the null hypothesis expected mean, which is the difference between two samples under the null hypothesis. Two sample means is almost always 0, so that's easy. For a one-sample problem, you actually have to think about it more. And so for hypothesis tests, it's the value that's expected if the null hypothesis were true. It's not taken from your sample. It's taken from the null hypothesis. And the standard deviation of the sampling distribution is otherwise known as the standard error. And we look that up with a formula. You just find the right formula and plug and chug. So a single mean hypothesis test, or a one-sample z-test, though we'll do it as t as well, which is much more common, follows the exact same pattern. You've got the mean from your sample. The point estimate from the sample is the sample mean. We might call it, sometimes we use the subscript observed to say this actually came from our data. And then you've got a null hypothesis value. And you're going to compare those two. The reason we compare them is because we want to know if the null hypothesis value represents a plausible explanation for where our sample value came from. It's similar to if this is Luke Skywalker and this is Darth Vader, and Darth Vader's like, I'm your father, and Luke Skywalker's like, that's impossible! I won't believe it. You can't be my father. He's like, yes, you came from me. Anyway, in the case of Darth Vader, the null hypothesis was actually true, something that we won't often know. The single mean hypothesis test, or one-sample z-test, or one-sample t-test, involves the mean of a single sample, and we compare that to the null hypothesis expected value, the value that we would expect the value that we would expect to be true in the population if the null hypothesis were true. Now, I'm gonna skip forward here. Oh, except I'm not. It doesn't like this. I guess we don't like next slide. So that null hypothesis, which I spelled totally wrong, hypothesis value, it could be a known population value. So for instance, you could say, we'll see whether our scores are significantly different from the national ACT verbal test mean score. We can look that up on the internet. We can find out what the average of American students is at getting what average score they get on that. It could be a value from a theory. So you could say Garcia's theory for this substrate suggests that under these conditions it should be 12.7 degrees centigrade, and let's see if our sample is significantly lower than that or something. The theory doesn't have to be a well-articulated scientific theory. It could just be something that somebody said. You could say Rush Limbaugh claims illegal immigration is a net drain on the economy. So your null hypothesis is that might be that the mean of this is lower than such and such because the claim says it's a net drain. Or it might be just a benchmark value. It's not from a theory, it's not from data, it's just something that sticks in our heads. For instance, we could collect some UTPA, GPA values from a sample of students and then say, is the mean greater than a B average? It's not really a theory about B averages necessarily, but we might have a reason to say B average. It just kind of has a place in our head. Let's see, is this bigger than a B greater than a B average? And there are reasons why we would do that sometimes, because they're just sort of psychologically meaningful points in certain scales. Another one is the history of the 1 minute mile, people running the 1 minute mile. So you could say, is our cross-country team's average faster than a 1 minute mile or something like that? And 1 minute mile was just a big psychological benchmark. So that would make sense under certain circumstances. So questions again, what's the sample point estimate for a one sample test? A single sample mean, a mean from one sample. What's the sampling distribution? All possible sample means that would have been sampled under similar conditions, but if the null hypothesis were true. What's the mean of that distribution? It's the mean of the null hypothesis, and there's no formula that can give that to you. You just have to think carefully and come up with a good one for a single sample situation. And what's the standard error? Well, there's two formulas. For a z-test, you know the population standard deviation, so it's this. For a t-test, it's the standard deviation from the sample divided by the square root of n minus 1. So the full setup is that you've got this sample mean. You wonder, where did it come from? I don't know. Let's assume, what if it came from this worst case scenario, the null hypothesis distribution? And if we want to see what are the probabilities that we would have observed this sample from that distribution, then we imagine all sorts of samples with the same sample size as ours coming from that distribution, and we place our sample there, and we say what's the probability that we would have discovered this, and the probability would be like this area here, or maybe that area plus a matching value on the other side for a two-tailed test. So we always want to get to this point. We always want to get to the sampling distribution that is implied by the null hypothesis, and then just put our sample mean in there in a meaningful way and figure out the area beyond our sample mean. The area beyond our sample mean is p, and if it's less than 0.05, you reject the null hypothesis. This pattern never changes. So you could say you're studying something that has to do with temperature, and because you have a sample size of 43, then your standard error equals 1.3 because you know what the standard deviation is, and your mean from a sample of 43 is right there, and so you found a mean of 27.3 degrees, and so there's your p-value, and it looks like it's greater than alpha, so too bad for you, no rejecting the null hypothesis. Let's say you have a sample of 249, and the mean of the null hypothesis is 89 years, so under the null hypothesis the average should be 89 years old for something or other. You figure out the standard error, you put your mean from a sample of 249, your sample is, oops, that's a mistake, that's supposed to be 72.3. It's lower. There might be some errors here. So you see these possibilities here. You're just taking your sample mean and putting it into these, I think obviously I've made some mistakes here, and you're putting it into these distributions, and you're figuring out what the probability is of finding your sample mean, or more extremely different from the null hypothesis mean. So let's run through an activity twice, once as a z and once as a t. The setup is that a drug company hears a patient reports that halitosis might be a side effect of one of their drugs. So they look at previous research. This is kind of a lazy, lame way to do this. It's like they should do a comparison study with two groups, but they're just going to use one. And you can sort of get away with this sometimes. Of course, you couldn't get away with an n of 9, which is what we're going to do, but this is a class, not a real research study here. Previous research that I made up indicates that on average people's breath stinkiness is a value of a mean of 60 on a standardized bad breath scale, so higher values are worse breath, and that the standard deviation of people's breath, if they're not on drugs, is 17.5 on that scale. So does the drug significantly alter people's breath on average? Now maybe the company hears these reports and says, well, let's look into this. We want to know if our drug makes people's breath worse, but what if it makes it better? We want to check both possibilities here. So two-tailed test, because if it makes your breath better, then rock on. Remember, high values are bad, just so that we kind of keep this straight. So here's the data they get from 10 participants. And you can see the mean and the standard deviation. These are breath scale scores. So we're going to follow this process. We're going to follow these steps here in doing a hypothesis test, a single sample hypothesis test. So we're going to do all these little thingies here, one at a time. Let's walk through this. What's the sample point estimate? It's 73.5, and it's a single sample mean, and it's on this variable that's the breath stinkiness scale, whatever that is. What's the sampling distribution? All possible sample means on that scale from n equals 10 in the world in which there is no drug. So the average of non-drug breath stinkiness. And what's the mean of that distribution? Well, we happen to know that it is 60. And what's the standard error? It's going to be the standard deviation of the population, which has been given to us, divided by the square root of n. So we write out our hypotheses. The null hypothesis is that the drug does not cause any change in breath stinkiness on average. And that's the same as saying, so just for this setup, that's the same as saying that the mean breath value of the population of all people who are on the drug is the same as the mean for those not on the drug. So we can just say if our sample mean is not significantly different from 60, then there you go, there's no difference. We don't have evidence to state a difference. And I don't know what just happened here. Here, just a second. I pressed the wrong button, obviously. Let's get back to where we were here. There. Sorry about that. So the diagram, and I use the computer to do this, but you can do it by hand. We do this diagram. It's a normal z distribution. In a two-tailed test, we put half of our alpha in each tail. So we have half of alpha on that side, half of alpha on this side. We don't have to put numbers there. I mean, this has numbers, but you don't need numbers yet. You could just do this without the numbers. You just know there's two tails. That's all you need to know. And you don't need to do anything else yet. To figure out what our critical z is, now you don't have to do this all the time. There are easier ways to do this. If you use the computer, you almost never need something like a critical z, but by hand you do. Critical z is left over from when you had to do everything by hand, and it can be a good exercise to think about things. So the way you do this is you look in your z table, and I'm just going to look in the negative z. It doesn't matter which one, because we're going to get one negative one and one positive one, and they'll have the same number. They'll just have a different sign. So I'm just going to hunt around in here until I find one of these numbers that says 0.025, because that's how much should be in one, there you go, in one tail of my distribution. That's half of alpha. And so I look and I say that's negative 1.96. So negative 1.96 and positive 1.96. In R, I can use this function qnorm, and I can just put in the value here to give me a negative number, and then I take the negative and the positive, and those are our critical z values. So now we can change our graph and update it a bit, and we can have our z critical, which is going to make your eyes bleed, but it says negative 1.96 and positive 1.96. So we've got to update it a bit now. Calculating z observed is pretty easy. It's just the difference between our mean and the null hypothesis mean divided by the standard error of the mean. And in this case, our mean is 73.5, null hypothesis is 60. There's the standard error formula. We work it out, and we find 2.439 if I did this correctly. Feel free to let me know if I didn't. So we can update our graph, and we can see where that should go. It's going to be in here somewhere, 2.4. So 2.44. So you can look at that. You can see you've just compared z observed to z critical. It's much easier with a graph than anything else. We're in the rejection region. Z observed is absolute value greater than z critical, and it's in the right direction, which in this case is either direction, because it's a two-tailed test. And that's our p-value, but that's only half of the p-value. Since we are using a two-tailed test, you always have to account for the other side. Now, you don't actually have to do these calculations. Just looking that z observed is in the rejection region, that tells you all you really need to know. P is less than 0.05, the end. But just for demonstration purposes, I'm showing you here that only half of p is on one side. Since we would have accepted results on the other side, we have to double our p-value as well, because we're accepting the negative p that would have, or the p that's on the negative side. P can't be negative. So we make a decision about the null hypothesis. We reject it. There's a number of reasons we can say we reject it. There's a lot of roads to get here. Because the absolute value of z observed is greater than the absolute value of z critical and in the right direction. Because z observed falls in the rejection region. Because p is less than alpha. these are all reasons that you could say why you reject the null hypothesis. And then your conclusion would be something like, the new drug does statistically significantly increase breath stinkiness. Poor drug company. In those who use it. And then you would put this little special statistical mumbo-jumbo afterwards to tell people what they need to know. Now, what if we did not know the standard deviation of the population? Then we would have to use the t-distribution and do a t-test, not z. And let's walk through this so you can see that it's really, really similar. It's almost identical. So, the same setup. But, actually, we don't know the population standard deviation. So, that's the setup. Making errors all over the place here. So we don't know the population standard deviation. We'll have to estimate that from our data, and as soon as you do that, you have to use t. So, same data. Let's take the exact same data, but let's just say we didn't have any estimate of the population standard deviation. So we have to use this one, 18.79, 18.8. So we're going to do the same process. We're going to walk through all the same steps. And the questions we ask will have similar answers. The sampling distribution of the mean will be a t-shaped distribution now, so we have to use a t-table for looking up both the critical and the observed values. But with t, we just use one table. The mean is the same. The standard error is calculated a little bit differently. The standard deviation of the population divided by the square root of n minus 1. Hypotheses are the same, exactly the same. The diagram, you could draw it the same, but I took the time to make sure it's a t-distribution. So you might just write t. Now I made it all accurate in t. You don't have to do that. Just make a curve, draw in some tails, shade them, and put t-distribution, whatever degrees of freedom. There you go. Make sure you got the right number of tails, etc. So finding the, I should say t-critical there. Finding the critical t, there are lots and lots of t-distributions, millions of them. So we just pack in tons of information into this table. So we just need to know the t to beat. We're not going to figure out our exact t if we're doing this by hand. And so for 0.025 in one tail, or 0.05 in two tails, and 9 degrees of freedom, the t to beat is 2.26 on both sides, negative and positive 2.26. Or in R, you could do qt, which is like q norm, 0.025, but then you have to add in degrees of freedom equals 9. You have to give it the degrees of freedom for t. So we can update our diagram, and now we have new t values. Notice that they've gone further away. 1.96, now it's 2.26. So it's harder to reject the null hypothesis now. And that's one of the consequences of not knowing things. You get punished for that. So calculating t observed is the same. It's just that instead of the standard deviation of the population, you have the sample. Instead of n, you have n minus 1. So we work through that. And that gives us a larger standard error, and therefore a smaller t observed value. It's not 2.44 anymore. Now the t value is 2.16. So we got punished in the previous slide by making it harder to find significance, and now we're getting punished here because we had a bigger standard error. And you often have a bigger estimate from the sample. You never really know. So we can update, I don't know why that spinning thing of death was there. We can update our graph and put t observed. So t observed is just a little to the right of the 2 value here. Anyway, it's not in the tail. That's all you need to know. It is not in the rejection region. So we do not reject the null hypothesis there. Now, if we wanted to really think about p, you're not going to do this with t. You're not going to look up p-values, but the computer might give them to you. And sometimes you have to remember to double things for a 2-tailed test or cut them in half for a 1-tail. So there's 1/2 of p, and of course we would have accepted the other side, so we have to use the other half of p as well. So p is quite a lot more than 0.05. So we fail to reject the null hypothesis in this case because the absolute value of t observed was less than the absolute value of t critical. If this had been a 1-tailed test, we'd have to think about the direction, not just whether the absolute value is greater or less, but the direction. If you put it on a graph, you don't have to worry about this. The graph shows you everything you need to know as long as you do it accurately. And t observed does not fall in the rejection region. This is just another way of saying the first point. And p is greater than alpha, which is another way of saying both of those things. So we do not reject the null hypothesis. And our conclusion might be something like, the evidence does not suggest that the new drug statistically increases breath stinkiness in those who use it. There's a million ways to say these things. The point is, you've got to say, we did not reject the null hypothesis, therefore we are not concluding that there is a difference. You're not concluding that there's no difference necessarily. That's a technical point, but you are not concluding that there is a difference. So next time, we'll talk about two means at once.